Hi, I'm Alison O'Connor, a postdoctoral researcher in the Mechanical Engineering Department at Imperial College in London. Today I'm going to be speaking to you about some of my work which looks at how we can estimate T0 for a low alloy structural steel, and specifically how T0 from Charpy correlations and T0 from the master curve method differ. This work was conducted with my colleagues Dr. Catherine Davies and Professor Steve Garwood and was funded by the Lloyd's Register Foundation. Structural integrity assessments conducted using fracture mechanics are used to determine the operational life of a component. Generally, we're concerned with preventing catastrophic failures like those associated with brittle fracture. Components manufactured from materials with low toughness will invariably have shorter operational lives compared to high toughness material. That's because fracture toughness is considered a key parameter in a structural integrity assessment. Fracture toughness testing is generally conducted using highly constrained geometries like single edge notch bend specimens, or SEMBs, like the one shown here. Constraint refers to the inhibition of plastic deformation in regions that are surrounded by bulk material, such as in the mid-plane or the mid-thickness of the specimen. While high constraint samples are used to predict conservative operational lifetimes, it does imply that our methods of assessment can be improved if we can fully quantify the relationship between constraint and fracture toughness. One method that's really useful for assessing how constraint might influence fracture toughness is the master curve approach derived by Wallen. The master curve defines the relationship between fracture toughness and temperature using a single point called T0 to define the movement of the curve relative to the temperature axis. So increasing, for example, the out-of-plane constraint by 10 times the original thickness will result in a T0 shift of about 60 degrees. Similarly, the in-plane constraint can be assessed using shifts in T0 to define changes in remaining ligament. In this way, the constraint effect can be adequately described by one single T0 parameter. So the main focus of this research is to compare T0 values calculated using Charpy correlations with T0 values estimated using fracture toughness data. And of course, we can't quantify either of those without conducting experimental work. Now, the experimental work in this project is based on an S275 grade material, a low alloy structural steel. And many of you will be wondering, why choose a low alloy structural steel? Well, the material choice is actually related to the wider implications of the project. Unfortunately, I don't have enough time today to go into the wider project aims and objectives, but if any of you are interested in that, feel free to contact either myself or my co-authors to discuss it. In this work, 3 different types of testing were conducted. Charpy impact toughness to identify the transition region of the material and estimate a T0 value. Tensile testing was conducted at each of the test temperatures listed here, and that was to define mechanical properties. And of course then fracture toughness testing was also conducted at the temperatures listed here for a number of different constraint parameters. Now, the in-plane constraint in our case was modified by using 2 different A/W ratios. So here you can see the highly constrained samples with A/W ratios of 0.5, and here you can see some shallow notched specimens with A/W values of 0.2. In order to assess the out-of-plane constraint conditions, specimen thickness was modified as shown here, and you can see here and here are the standard geometry types that are accepted by most fracture toughness testing methods. All other geometries are considered non-standard geometries. Okay, so here we can see the relationship between Charpy impact energy and temperature. So a number of different test temperatures were tested from plus 100 degrees all the way down to minus 70. At each test temperature, a minimum of 3 samples were tested from which an average measurement of impact energy at that temperature was defined. The upper shelf region was fitted to the averages using simple linear regression. The transition region was fitted using a 2-degree polynomial. Now, in the transition region, we've defined the transition temperature as being the mean of the upper and lower shelf values. We also defined the temperature at which we reached 27 joules and 41 joules. Our Charpy toughness data allows us to make an initial estimate of T0 using our T27 joules, which was minus 47, and our T41 joules, which was minus 43. Now, in this case, I've assumed a 1-inch thick specimen to derive what the constant C values are. Other data are given in the test standard, and you can refer to those for different thicknesses. In this case, our T0 is estimated to lie between minus 65 and minus 67 degrees Celsius. So further fracture toughness testing was conducted at minus 70 degrees in order to be able to reassess T0 more accurately from our fracture toughness data. Before we get to the fracture toughness data, this is a brief look at the tensile test results. 4 specimens were tested per temperature. Each specimen was analysed individually to assess the Young's modulus yield and the UTS values, and then the results for those 4 tests at each temperature were averaged to populate the table you can see here. The results were as expected, with the yield strength increasing as the temperature decreases. These videos show strain perpendicular to the notch for a low in-plane constraint condition and a high in-plane constraint condition. The measurements were made during room temperature fracture toughness testing on standard B by 2B size specimens using digital image correlation. So the only difference in these 2 specimens is the in-plane constraint. Now, it's interesting to note that initially the strain profiles are similar for both conditions, but as the test continues, the low constraint sample absorbs more strain over a much wider area compared to that of the highly constrained sample. Now, that's not unexpected, given that low constraint samples tend to generate higher measures of fracture toughness when compared to their high strain counterparts. And of course, fracture toughness, or J, is calculated as the area under the curve. So if I have a longer ligament, I'm going to have more area under the curve, which is likely to give me a higher measure of fracture toughness. And that is indeed what we see here. These plots are for the shallow notch specimens and the deeply notched specimens. The symbols that are shown here are for each individual specimen geometry, so the out of plane condition or the thickness effect. At each test temperature, a minimum of 2 samples per thickness was tested, and the data points plotted here are the average of those 2 values. What's interesting to note is that the deeply notched samples predict much lower fracture toughness values when compared to the shallow notched specimens. This is as expected. Now, for the master curve method is relevant only to steels that have failed in a brittle manner. So if we remove from these 2 plots any data that have failed in a ductile manner, our tests reduce to this. Here we can see that almost all of the lower constraint samples have failed in a ductile manner, even at very, very low test temperatures, whereas the highly constrained samples almost all failed in a brittle manner, even at test temperatures that are relatively high. Now, if we disregard these low plane constraint samples for the moment and focus purely on those in the high constraint condition, we can convert these average JM values into stress intensity factors. In this plot, we've converted our J values into KJC, our stress intensity values, for our highly constrained samples, all of which failed in a brittle manner. And what you can see is that while there's some indication that fracture toughness changes with regards with respect to temperature, there's a significant amount of scatter in the data. This, of course, is due to the changing out of plane constraint or thickness effect. Luckily, Wallen derived an equation which allows you to modify your KJC value to a standard specimen thickness. In this case, we've chosen a thickness of 1 inch. So if we apply that conversion to our test data, what you can see is that the scatter is reduced quite significantly, and now the relationship between test temperature and KJC becomes much more clear. And you can see that as the test temperature decreases, the fracture toughness also decreases. There are a number of ways of calculating T0 using standard guidance. Our Charpy correlation showed that our T0 estimation was in the range of about -70. So using the -70 fracture toughness data generated in the previous slides, we can apply these equations here to estimate what T0 should be, and that comes out to be a value of about -107. Another method looks at iteratively solving T0 based on the number of data points and validity limits. Using that method, the T0 was calculated to be approximately -107.2, and we fulfilled all the validity requirements. Hence, the T0 value for our material is estimated to be -107.2. Now that we have our T0 value, we can apply the master curve relationship to calculate the median upper and lower bound toughness as a function of temperature. What I've plotted here is the individual test data compared to the upper, lower bounds, and of course the median curve. Interestingly, some data fall outside of this lower bound toughness curve, but it should be noted that the median upper and lower bound curves are based on the average calculations for KJC, whereas what I'm plotting here are individual temperature values. So if you look, for example, at this X here, you have another X here, the average is actually going to be above this lower bound toughness. Similarly for the B = 20 or the red triangles, the average toughness for this sample is likely to be here, which again puts it above this lower bound curve. So in terms of T0 then, we estimated from Charpy data what our T0 would be, and we came out to have approximately -66 degrees Celsius. Looking at individual test data at -70, we got -178.68, and then by applying the iterative analysis and using validities, we showed that the valid value of T0 is actually -107.2. So both of these methods give you very similar T0 results, and the Charpy estimation gives you an extremely conservative estimation of T0. To conclude this work, we can say that shallow notch specimens, i.e. specimens with low in-plane constraint conditions, will have higher measures of fracture toughness compared to deeply notched specimens. The Charpy impact energy predicted the T0 value to be approximately -66 degrees. Fracture toughness testing was then conducted at -70 degrees Celsius, and the T0 value was re-estimated to be closer to -107. This result was validated. The T0 value estimated using fracture toughness data was significantly lower than that predicted using Charpy estimations. This means that predicting fracture toughness from Charpy correlations will significantly underpredict component lifetimes. Thank you very much for listening. I hope you enjoyed the presentation, and I wish you the best of luck with the rest of the conference. Future work on this project will aim to incorporate finite element modelling, specifically looking at the T-stress values and estimating low constraint toughness using a finite element model prediction of T-stress and high constraint fracture toughness data. Those estimations of low constraint toughness will then be compared with low constraint test data generated as part of this work. Thank you.